Hi everybody. This video is about time domain design. So we are looking into requirements to a control system in a time domain and how they have impact on the design in the S domain. Well, mostly we have three requirements on the time domain, which is the overshoot, the settling time, and the offset. And suppose we have at least a second order system and we apply a step to it, we see a kind of response which looks like this. And we have probably requirements to the maximum overshoot, which occurs over here, the settling time, so how long it takes before the signal has damped out, and to the offset, which is the static error. So we're going to look how these three specifications will be translated into requirements for the design in the S domain. So first of all, let's look to the general transfer function of a second order filter. It says it's omega 0 squared, which is omega 0 is the undamped angular frequency, so squared divided by s squared plus 2 times beta times omega 0 times s plus omega 0 squared. Beta is the relative damping coefficient. And in order to have overshoot, because we have requirements to overshoot, the beta should be smaller than 1, of course, because when beta is higher than 1, it's larger, then we do not have overshoot. And in general, we also have a static gain over here. So we can, based on this transfer function, derive the poles, which we can derive by setting the denominator to 0. And when we apply the ABC formula, then we get that the poles are located at the following position. It's minus omega 0 times beta plus or minus j times omega 0 times the square root of 1 minus beta squared. And that is a complex number in which this is the lambda, which is the absolute value of the damping and which is the real part of the pole, plus j times the omega. And this omega is the damped angular frequency and it's the imaginary part of the pole. All right, so now let's look what happens when we apply a step input to that system. When we do that and beta is smaller than 0, we get a so-called exponential harmonic signal, which is equal to an amplitude A times 1 minus e to the power lambda times t times the cosine of omega times t plus an angle phi. In this case, the lambda is the absolute damping, and the omega, which is here, is the oscillation frequency, the undamped, so the damped oscillation frequency of my signal. And the signal response looks like this. Well, when we have this response, we can define the overshoot. When we have this measurement as the maximum value, the peak value over here, minus the end value, so when everything is damped out, and that related to that static value when everything is damped out, and often in percentage, and then we multiply it by 100%. So that is the overshoot which we can define from a measurement. What you also can do is when you have this signal description, you can take the derivative, which gives you the impression for Tp, the peak time, and fill that in, and then you get an expression for the maximum value, which is the overshoot. And when you do that, it seems that the overshoot is equal to e to the power minus the absolute value of lambda divided by omega times p. So what does this tell us? It's e to the power minus the absolute value of the real part of the pole divided by the imaginary part of the pole times p. So when I know the pole locations, then I can calculate the maximum overshoot of the signal system response when I apply a step input to it. So again, the overshoot is equal to the division of the real part of the pole divided by the imaginary part of the pole, absolute value of it with a minus times p, and that value e to the power that value. So there is a relationship between the real part of the pole divided by the imaginary part of the pole and the overshoot. Well, we have also seen that lambda has been defined as minus the omega 0 times beta. And the omega, the damped angular frequency, is equal to omega 0, the undamped angular frequency, times square root of 1 minus beta squared. So we can replace the lambda and the omega by these expressions. And then we get the expression over here. So we can get rid of the omega 0 here in the numerator and denominator. And then we see that there's also a direct relationship between the beta, the relative damping coefficient, and the overshoot. Okay, the peak time can also be calculated. When we take the derivative of this function, we get an expression for the peak time. And the peak time is the time where the overshoot occurs. And that is equal to a simple equation. It says the peak time is P over omega. So the P divided by this damped angular frequency. So again, we have calculated the overshoot and we know the values of the poles. And suppose we know the lambda and the omega from our transfer function. And when we know that lambda time over omega is 1, we can calculate the corresponding beta value and we can calculate the corresponding overshoot when applying a step signal to the input. And this value of lambda over omega yields an overshoot of 4%. When lambda over omega is 0.7, then the overshoot is 11%. And when lambda over omega is 0.5, then the overshoot is 20%. So that brings us to a interesting thing which we can see over here in this picture of the S-plane. Well, when we draw lines which have a value of lambda over omega, which is a constant value. So, for instance, in this example, the absolute value is 1, so minus 1 here and 1 there. It means that systems which have poles lying on these lines always have an overshoot when applying a step to it, to the input, an overshoot of 4%. So when I have a system with two poles over here, the overshoot after applying a step set point is 4%. When I have another system with poles over here and one over there, it still has an overshoot of 4%. So by knowing the value of lambda over omega, it defines what the overshoot of the system response will be. So it's corresponding to the relative damping, also the lambda over omega line. When I have another value of lambda over omega, for instance, it's minus 0.5, then the overshoot is equal to 20%. So you see, when you have a steeper line over here, the overshoot increases. So when you have a pole on this line and that line, it has the same overshoot. And when you have poles which are on these lines, they also have the same overshoot, but corresponding to this value. Suppose we want to design a system, and we have a system requirement that when we supply a step set point to the input, that the overshoot may not be higher than 4%. Then we can calculate what the value of the lambda divided by omega may be. So we can define an area in the S domain where the poles may not be in order to apply to this requirement. Well, when the overshoot is 4%, at the maximum value, we can say e to the power minus lambda over omega times p times 100% has to be smaller or equal to that 4%. Or we can also say minus the absolute value of lambda over omega times p has to be smaller or equal to the natural logarithmic function of 0.04. And that means that the absolute value of lambda over omega, the absolute value of it, should be larger or equal to minus the natural logarithmic function of 0.04 divided by p, which is almost 1. That was the corresponding 1 in the table. So these poles may be on this line, but they may not be in this area. But because remember, when a pole is, for instance, on a line over here, then we have seen that the overshoot increases. So the poles may not be in this area. And of course, they may never be in the right half plane because then I have an unstable system and my signal response keeps on rising and rising. And of course, the overshoot is infinite in that situation. So this is the forbidden area to comply to that requirement. All poles should be on this line or to the left of these lines. And when they are to the right of these lines, then I do not comply to this overshoot requirement. Okay, now let's look to another requirement in the time domain, and that could be the settling time. And the settling time is the time it takes before a transition phenomenon remains within the set limits around the final value, so due to static situation. So, for instance, when we want to have the signal within 5% around its end value, then we can define the settling time, and that gives us an indication at which point in time the signal stays within these limits. And we often use two types of settling times. The first one is the response time, which is the 5% settling time, which is depicted over here. And we can also define a 2% settling time, which is depicted over here. And then the signal should be within the green boundaries. And of course, that time, which we also call the indication time, that 2% settling time, that indication time is always higher, of course, than the response time, the 5% settling time. Okay, when we know that, we can also see whether or not we can calculate the corresponding values of the poles. Well, looking back to the exponential harmonic function, this was the exponential harmonic function. This part, e to the power lambda t, defines the damping. So it defines how quickly this signal damps out to a constant value over here. So when we want to look to the 2% settling time, we have a requirement to e to the power lambda times t, and that should be smaller than 0.02. Or we can also calculate the settling time. That should be at least when it's equal to 0.02, then it's the natural logarithmic function of 0.02 divided by the lambda. So the natural logarithmic function of 0.02 is almost equal to -4. So we get an expression which says that the 2% settling time, which is the indication time, is almost equal to -4 over lambda. We could get or create a similar calculation for the 5% settling time, which is the response time, and then we see that that response time is almost equal to -3 over lambda. Or what we see is that there is a direct relationship between the value of the lambda and the settling time. And remember that lambda is also the real part of the pole. So there is a direct relationship between the real part of the pole and the settling time. So when we want to make requirements to that settling time, we have to make requirements to that lambda over here. And when we plot again the S plot with the lambda, the real part over here, and the j omega, so the imaginary part of the pole over here, we see that all poles which are lying on the same lambda line have the same settling time. So now let's look to a requirement. For instance, we require that after applying a step set point to a system, that the 5% settling time should be smaller or equal to 1 second. Then we can calculate the forbidden area, because the 5% settling time is equal to -3 over lambda, and it should be, in this case, not be higher than 1 second, which means that the lambda should be smaller or equal to -3. So, well, this is my S domain again, so we can draw a vertical line, so a line at which all values of lambda are constant, and we can say, well, these poles may not be to the right of this line, because when they are to the right of this line, my settling time increases, which is depicted in this table over here. For instance, let's see, when lambda is -2, then the settling time increases increases to 1.5 seconds, and when lambda is -1, the 5% settling time increases even to 3 seconds. And of course, when the poles are over here, we have an unstable system. So the poles may not be to the right of this vertical line when applying and meeting this settling time requirement. All right, now suppose that we have a double requirement. I have an overshoot requirement and I have a settling requirement. Well, then I have a requirement to the lambda over omega line, which was corresponding to the overshoot requirement, and I have a requirement to the lambda, which is corresponding to the settling time. So in the S domain, these are the lines corresponding to a constant value of lambda over omega. And in this case, lambda over omega is the absolute value is 1. So the poles may not be to the right of this line to comply to this requirement, but they should also comply to this requirement. So the poles may not lie to the right of this vertical line. So the complete forbidden area for systems to comply to both requirements, this forbidden area is the dashed lines over here, the right of both curves, both lines. So these are the overshoot and settling time requirements translated to requirements in the S domain. Last but not least, we have also the parameter offset. And offset is the static error of my system response. So when I apply a step to my system, I have a static error. I have an error over here, and static error over here is called the offset. And when I have this graph over here, I can define the static error here at the end, where the signal is static, so it's not varying anymore, it's constant. So the static error in this plot is this value. So I can say the offset is the static error referred to the step value A. So it's A, the step signal value, minus the output of my system in the static situation over here, divided by A. And when we have an offset definition in percentages, we have to multiply it by 100%. An example, if A is 20, I put a step of 20 to the input of my system and the end value in a static situation. So when every phenomenons have damped out, that static situation, the value is 18, then the difference is 2. So the offset in percentages is 2 related to the step value of 20. So 2 over 20 times 100%, which is equal to 10%. Okay, we can also calculate this offset, because suppose that this error is my output of my system. And then I can say the relationship between the output, the error, and the input, my reference over here, is what we also do when we look to the output of my system over here, is every block in the straight line divided by every block which is in the loop. So in the straight line from reference to error, the transmission is 1. And in the loop, we see the blocks Kr times HP. So in the denominator, we have 1 plus the open loop. So it's 1 plus Kr times HP. So that is what we also call Kr times the loop HL. And that is written over here. So again, it's a straight relationship from R to E, which is 1 divided by 1 plus everything in the loop. So HL. But we want to look to the static error, to the offset, the static error. So in a static situation, my value is constant and the derivative of a constant value is 0. So in my transfer function, I can set all s's to 0, because s is the derivative. So I have to look to 1 over 1 plus the transfer function in the loop when setting the s to 0. and that is also called 1 over 1 plus the loop gain, static loop gain over here. All right, that's it. That's all about defining signals and defining requirements in the time domain and defining the corresponding locations of the pole in the S domain. Thank you for watching, and I see you next time.